This is the Earth Science Classroom. Welcome back to the channel. This video is on oceanography and we're going to discuss the thermocline. This is the Earth Science Classroom. Welcome back to the channel. In this video, we're going to answer the following questions. What are the three oceanic layers? What is the thermocline? How does the thermocline form in the oceans? And what is the difference between permanent and seasonal thermoclines? When discussing the thermocline, we must first discuss the three main oceanic layers that occur within the water column of a big body of water, a large lake or an ocean, whereby the three layers are separated due to stratification and the layering caused by the characteristics of each layer of water or water mass. The top layer is called the mixed layer, also known as the Ekman layer. The middle layer is the thermocline, and the bottom or third layer is called deep water. Now, the mixed layer or the Ekman layer is a interacting layer between the thermocline and the atmosphere. This results in direct surface forcing between the atmosphere and the ocean surface in regards to wind stress, which involves fluctuations in both salinity and density, and also solar radiation and the absorption of heat. And as a result of these differences or characteristics, the stratification of the ocean to create these three distinct layers is down to the water mass's density. As mentioned previously, the world's oceans are divided in a vertical water column into three layers. The top mixed ocean layer, or the surface layer, which is called the Ekman layer, then the thermocline, and then the deep water. Now, this thermocline is a transition or transient layer which can change in depth and change in strength, but it is defined as a rapid decrease in temperature with increasing depth. So over this layer that's sandwiched in between the warm surface layer and the very cold deep water, you have this rapid change from hot to cold within this vertical water column. And this thermocline plays a very important role in the world's oceans in terms of heat transport, the global budget of heat, and the interaction between the ocean and the atmosphere. Now, this thermocline is an example of stratification where the water becomes layered based on the characteristics of that water, which basically comes down to density of water, where the deep water is extremely cold of around 2 to 4 degrees on average, but does get colder in the deep ocean trenches. But from around 1,000 meters down, you get the deep water, and it's a consistent cold temperature. Then we have the upper layer, the mixed surface layer, which on average is around 17 degrees Celsius, which is equivalent to 62 degrees Fahrenheit, which again can range where you have colder towards the poles, and around the equatorial oceans you have a much warmer, but on average around 17 degrees. So you're going from an average of 17 in the mixed layer, where you have a very slow change in temperature with depth, and it goes to a depth of about 200 meters where you hit the thermocline, and that temperature drops quickly with depth down to 1,000 meters, where it goes from a warm temperature down to a very, very cold temperature. And this layering or stratification is consistent throughout the world's oceans and is the permanent thermocline. Now, the word thermocline itself, the word thermo or thermos, comes from the Greek, which means heat or warmth, and then the word cline means gradient or slope. So it's a change, or how fast the rate of change in temperature throughout this layer in the ocean between 200 meters down to 1,000 meters on average. Now, as mentioned before, it is a transient layer and a transition layer which can separate the warm surface from the very cold ocean depths. Now, on average, the thermocline, or the point under the ocean where the temperature changes rapidly with depth, usually begins at a depth of around 200 meters. However, it can become shallower or deeper based on different characteristics. One of those characteristics is the strength of the thermocline, which means the rate at which temperature decreases. So the faster the temperature decreases over depth, the stronger the thermocline, and that would present a stronger, more resilient barrier between the warm surface layer that's mixed uniformly and the much colder isothermal deep water below the thermocline. And this strong thermocline acts as that strong boundary layer which prevents any mixing of the surface layer becoming deeper. So a strong thermocline would be closer to the surface or shallower, compared to a weak thermocline where you have a slower decrease in temperature with depth. So it doesn't get as cold as quickly in terms of depth. Then you'd allow the mixed surface layer to have increased mixing and vertical distribution. Therefore, it would lower the boundary between the mixed layer and the start of the thermocline. So this would be a deeper thermocline. But the average in terms of the thermocline depth starts around 200 meters. The permanent thermocline is a direct result of deep water circulation across the world's oceans and the formation of stratification due to the temperature of the water from the surface down to the bottom of the oceans, creating the three layers, with the thermocline being that transition layer, that transient layer, whereby it moves in terms of its depth and where it starts and where it ends. But the fact remains that it is an area of the ocean where the temperature rapidly changes with depth. In this case, gets colder quickly as it goes deeper into the world's oceans. Now, on top of this permanent thermocline, towards the mixed layer, surface layer, you have what's called a seasonal thermocline, which by definition is affected by the amount of solar radiation due to the tilt of the Earth and the seasonality of that location. So we know that the mid-latitudes between 30 and 60 degrees north and south experience the most seasonality on our planet, and you go towards the polar regions or the equator, the seasonality is going to decrease to the point where you don't have seasons. You have just one consistent condition, whether it be in the atmosphere or in the world's oceans. So the seasonal thermocline is in addition to the permanent thermocline, which occurs towards the surface and can fluctuate where the thermocline begins and ends in terms of the bottom of the Ekman layer, surface mix layer. Now, for the winter in the mid-latitudes, we're looking at a very small difference in solar radiation throughout this season, this period, and therefore you're going to have a small difference between the surface layer and the deep water, so the thermocline becomes very weak and a slow, gentle gradient between the surface layer and deep water. When it comes to the spring, the seasonal thermocline is going to react with increased solar radiation, increased thermal energy added to the surface layer of the oceans, and this is going to also increase wind stress and the wave-driven mixing within the shallow depths of the ocean, and it's going to increase general vertical mixing of the warm surface layer, and this is going to create a stronger thermocline based on the difference between the warm surface water and the cold, more consistent isothermal deep water, which means that the bottom of the mix layer is going to rise up and the thermocline becomes shallower, so a decreased depth of where you see this change in temperature. Then we get the summer, which is going to extend the solar radiation and heating of the surface ocean layer and maintain that shallow thermocline. It comes to the fall or the autumn, and you get that change of solar inclination, the change of angle, and the reduction or decrease in solar radiation, which is going to have an effect on the thermocline. The mixed surface layer or the Ekman layer becomes colder and reverting back to that deeper thermocline with a more gentle temp difference between the mixed layer and the deep water layer. So throughout the year in this upper part of the ocean stratification, and above or near the top of the permanent thermocline, you have these seasonal changes based on the amount of heat being added to the mixed surface layer and how the thermocline is going to adapt and either ascend or descend based on the heating. So as I mentioned before, the high latitudes, the areas of the oceans around the Arctic and Antarctic, are going to have a consistent thermocline, more like the permanent thermocline we see through the whole water column. However, in the tropics, because of the increased heating, it's more consistent throughout the year with limited or no seasonality. What we find is what's called a tropical thermocline. The lack of cooling is going to create a very strong thermocline, beginning at a depth of about 100 meters, extending down to 1,000 meters, where you have that large temp difference between the upper mixed surface layer and the deep water. This is the Earth Science Classroom. Thank you for watching the video. I really appreciate it. And if you get a chance to like and subscribe, that stuff really helps the channel. Thank you so much. And see you again in a future video.
Have a great day. Bye.